perfect watch for the English, and I leave the microphone to Mir for the beginning of the meetup.
Hello, hi everyone here, and hello to everyone who is watching us on streaming. So, welcome to our 32nd Milan Bitcoin Meetup. Tonight, the first part of the meetup will be totally made in Italy, explaining a very important event that will hold place in our office from tomorrow to Saturday, the Hackabit. 2 days of workshops and a hackathon for the real use cases for Bitcoin, notarization, and smart oracles. The event is organized and run by Eternity Wall CEO Riccardo Casatta and Oraclize CEO Thomas Bertani, and they will explain everything later. Also, for the international part, we are honored to introduce you Andrew Poelstra, mathematician at Blockstream, mostly famous for his recent works on Mimblewimble and confidential assets, and also world-class champion of the Legend of Zelda video game. So, tonight is going to explain us how something similar to Coin's script can be implemented on systems like Mimblewimble, even without a real script. The script-less script, crypto magic. Then, well, once again, Peter Todd. Of course, I'm only joking. We are very happy to have him with us again. He will talk about open-timestamping-archive.org, and he promised us that something historic is going to happen. And I really hope so, because I personally donated something like 1,000 bits for his ICO. After all the talks, the Q&A session for all the speakers, so please keep your questions for the end. And after that, I would like to ask to other special guests if they want to come here and say hi. We have here between the crowd Adam Gibson of Gen Market, Pavel Krachenko from Ukraine, that we have an open account meetup at BHB tomorrow, and Ken Shishido, that you already know, Tokyo Meetup organizer, and also investor in many interesting Bitcoin projects. So we have an hashtag for this meetup, 42BTC. If you want to share something, be sure to add it. Next meetup will be on 7th of June, and the guest will be Lalo Rosbeef of Lightning Labs. Okay, let's start. I invite here Riccardo Casatta and Thomas Bertani. And in meanwhile, I'll give you some practical info about the Hackabit that will be at the BHB Network offices here in Copernico at the third floor, or as an online webinar. Just a quick reminder, the hackathon will be in Italian, but tonight everything about it will be in English. The agenda of the event is on the 11th of May, tomorrow, from 6:30 p.m. to 8:30 p.m. Riccardo Casatta will have a workshop about timestamping. The day after, at the same hours, Thomas Bertani will have a workshop about conditional escrow address in Bitcoin. So let's stay this time from 9 a.m. to 8 p.m., so the full day, will be hackathon will take place. First prize for the winning team, 1 Bitcoin for all the team, plus 1 ledger hardware wallet for every member of the team to keep safe the prize. Okay, now it's time for you, Riccardo.
Thank you very much, Mir. So I'm Riccardo Casatta. I'm the founder of Eternity Wall, and today we are gonna see what's timestamping in the first place. Otherwise, who comes to the hackathon? So we are gonna see from the origin of timestamping, from the postmark, and how we can use the blockchain for timestamping, and why we use the blockchain. And then we are gonna see the agenda of tomorrow. So to know what will be the workshop about. So what's timestamping? It's just giving a certain date to a document. For example, the postal mark of the postal office with a little point of attention. The postmark must be on the document itself, not on the envelopes. Otherwise, you can put in the envelope whatever you want. In civil law, so like the law here in Italy, dates on important document must be made by public official. For example, the notary, if we are buying a house. But what about digital documents? So we have digital timestamping, which is based on digital signature of a third party, and which is based on a certification authority. One classical example in Italy is the PEC, which is the electronic certified mail, which is already a timestamp by itself. But how we can use the blockchain for timestamping? So this is time, and these are blocks which reference each other. We have a genesis block at time t0. Basically, miners put the timestamp inside the block. If they go to, if the timestamp is it's too away from the real time, they risk that other miners don't mine on their blocks. So they have an incentive to do a proper timestamp. In Bitcoin, this is plus or minus 2 hours. So at a certain time, we take a document, we make an hash of it, which generates a statistically unique fingerprint of the document. We put this data inside a transaction, which goes inside a block, and we just timestamped that document because it's inside a block at time t3. So this is a proof of existence of this data at time t3, which is the time of the block. And afterward, many blocks came. Blockchain is made so that it is immutable for the incentive, and that's it. So why we use the blockchain, which is, we already have digital timestamping, by the way. So because digital timestamping requires third party, and this is why it's always sometimes called trusted timestamping, and this increases cost. And requires digital signatures, which requires to store a secret, and this increases risks. So let's talk a little bit more about this last point. So what if the timestamper's key is stolen or the certification authority key is stolen? Well, no problem. You can just issue the revocation certificate of the key and consider timestamps after the theft unsecured. Right? Clap. This is wrong because every timestamp created by that key had to be considered unsecured because the thief can simply backdate timestamp. He owns the key, so it can just invent some time, sign it, and that's it. So timestamps digitally signed are as safe as the key signing the timestamps. So again, if this is the time, I have a digital timestamping here. There is a theft, there is an hack of the authority. Hack happens, we see it many times. So not only the timestamp after the theft have to be considered unsecured, but all the history. So when I think about the digital timestamping infrastructure, well, I think about this castle of cards. If an hack happens, what do you think will happen? Like that. So okay, this is trustless timestamping. Trustless is not a bad word. It's just you don't require trust in the timestamping provider. Does not require a secret, so no castle of card going down. And could be aggregated. So could scale as much as we want. There is no problem of the transaction fee that we see nowadays in the most crowded blockchain, because you can fit, maybe we see something later on, a lot of timestamp in just one transaction. There are many possible use cases for regulators in the supply chain, healthcare, info security, legal, insurance, and it's up to you. We'll see at the hackathon. And there is also a proposed standard for timestamping, which is open timestamps. That's it. So that was the presentation about timestamping, and now we're going to see what the hackathon will be, which is this will be the workshop tomorrow evening, like Amir said, from 18:30 to 20:30 here at the floor. So we are going to start just a little bit of history of Eternity Wall from the message lasting forever, and then focus on timestamping. We are going to see again the presentation we done here, because maybe someone missed it, just with a little bit detail more. We are going to see the team of the timestamp of Eternity Wall. Then we're going to concentrate about a lot of use cases you can do about timestamping, so you can get inspiration for the work of the hackathon. So you can use, like I said before, for regulators, like an answer of digital signature, for evidence authenticity, record integrity. We're going to see a surprise from Peter later on. And, well, it's up to you. That's one of the purpose of the hackathon, which we want to see experiment and use cases for timestamping. We're going to see open timestamps. What is it? We're going to see the detail about the Merkle tree that allows you to store a lot of timestamps inside just one transaction, which is the same system that Bitcoin used to prove a transaction is in a block. And we're going to see the architecture, so all the entity that how the entity works together, how the blockchain is involved, the receipt, the format of the receipts. We're going to see the client, the calendar servers, and the backups to achieve the property we want for a good timestamping service. And then we are going to see an hands-on. I'm quite happy there are already 4 language libraries for open timestamps. The first one in Python, then there is JavaScript, Java, and the last Rust. We're going to see the cycle of stamp, upgrade, verify, like really an hands-on. So on your laptop, you're going to try the library, all thing that works. You're going to see. So thank you.
Hi, hello to everyone. So it's a pleasure for me to be here again. I will try to stay high level during this presentation, so I will not dive too much into the technical details. This is because we will do that on Friday during the workshop. So the workshop is meant to be attended by developers. So first of all, let's see what Oracleize is. This is a project I started a couple of years ago. Today we are 8 people in London. We are working on trying to secure the feeding of data into smart contracts. So I hope that most of you already know that smart contracts are definitely not smart and not contracts. So I proposed a completely different naming for our integration on Bitcoin, but unfortunately, can we keep this out from the recording? But most of our clients today are using our service on Ethereum, where smart contracts have this specific naming. So during the first part of the presentation, I will stick with that. So here you see some kind of use cases that people are building. So those use cases are like applications that are out there in the wild and that people are using to solve some kind of problems, like the transparency in online gambling, for example, or payments. Well, of course, Bitcoin solves the payment issues itself, but it doesn't solve some other issues. So let me try to dive just for a few seconds into each of those, because I think they all have something to teach us. So the first one is decentralized gambling. So we know that with traditional centralized online platforms, well, you need to get a license, right? So you need the state to approve that your platform is safe. And myself, I decided to waste some of my time to read this, the requirements of those certifications. And it looks like they come from the 80s. They have no clue of what IT security is about and things like that. So what decentralized gambling is about is trying to get rid of intermediaries and trying to have well, a process which is as transparent as possible to have, two people interacting and some kind of randomness in between, which is choosing who is winning, right, at the game. So think about throwing a dice or something like that. So there are many projects today. I will not name them, but probably you already know some of those that are based on Oracleize and that on Ethereum use Oracleize as a way to connect external sources of randomness to the smart contract that sits on the top of the Ethereum blockchain. Another use case is the one of payments using digital identity cards, like the Estonian ID. So the Estonian ID is a national ID card that anybody can get regardless of the nationality. And it's interesting for me to, integrate this card with something like an Ethereum smart contract, so that you can use it as, your as an Apple wallet, basically. So you can use it to store your funds, and you don't have to deal with all the complexity of key management and so on. So you can have a smart contract to do that on Ethereum, and this is what we built during the last few months. But there is still a need for external data even in this scenario. And the external data here, of course, is not a signature, because the signature is something that you can push to the blockchain, and anybody can push a signature to the blockchain, and it can be verified by itself. The validity of the signature is trivial to verify, but something that you still need to get from some external source of data is the validity of the status of the certificate. So you want to know if the given ID card was stolen or not, because you don't want a thief to run away with your money, even if he provides a valid signature. Our third use case is like peer-to-peer insurance, where think about something simple like flight delay policy, where a smart contract keeps monitoring the status of a given flight and just pays out accordingly. So these are all things that are already implemented, that are pretty much working and based on Oracleize. So I will not dive into the way Oracleize works, but we try to provide a secure channel, an authenticated channel, to connect any data source out there. So think about any provider of data, any web API, with smart contracts on the different platforms. Different platforms means that we are agnostic to that. So regardless of my personal opinion, which is not that important, we are integrated with many because the value of our system sits in the off-chain part. So Oracleize itself is using some techniques to ensure that this connection is valid, is secure. So it's enforcing the authenticity of data in a way that is fully verifiable. And we have an integration with Bitcoin, and we were looking for some feedback, so we thought that it was exciting to just propose a workshop first and then an hackathon to see what people's opinion was, and to see if there was any interest in using it for some kind of use cases. So, yeah, I just said that I don't want to dive into this. So, yeah, let's keep this slide. So the Oracleize Bitcoin integration, again, is not about smart contracts, right? It's about what we call conditional escrow addresses. So what they are is really a way to commit the Bitcoin address. It's technically the redeem script to a set of conditions that are verified off-chain in an authenticated way, again, so with the same technology which we are using with the other blockchains. And what it does in practice is binding a given Bitcoin address to those conditions, so that you cannot spend the Bitcoins that you send there unless something happens. So you can have something like a Bitcoin address which commits to the temperature in Milan, so that if anybody sends Bitcoins there, they cannot be moved unless the temperature goes above 20 degrees, something like that. Or you can maybe use it for the same use cases we've seen before, like gambling or things like that. So you can have a Bitcoin address which tries, even with non-deterministic processes like throwing a dice, to release the funds just if that condition is verified. And there is a specific way, of course, to commit the address and the signature to the condition that has been verified, and to enable a full authenticity a full auditability of the entire process. So this is pretty much it. If you're interested in diving into this for, how long is it, 1 hour and a half? 2 hours. We are doing this workshop. So tomorrow we have the Eternity Wall 1 around timestamping. The day after, so it's Friday, we have the one around the Oracleized Bitcoin integration. And the day after that, so on Saturday, we have the hackathon, in which you are free, of course, to play around with those two tools or with whatever else you like on Bitcoin, please. Thank you.
Hi, I'm Andrew Poelstra. I'm a mathematician at Blockstream, and I'm going to talk about this thing called scriptless scripts, which is a new way of thinking about smart contracts and a new way of implementing smart contracts that has much better privacy and efficiency properties than other ways. So I'll get started. So scriptless scripts, what this is, as it sounds like, it's a way to do smart contracts or scripts or however you want to call them without actually using scripts. What we want to do is execute a smart contract, which is you've got a bunch of parties, they agree to send some money to each other or do some things, assuming some conditions are satisfied. But we don't want to do this by having an explicit script on the blockchain that everybody looks at and everybody verifies. Ideally, what you want is somehow for the blockchain to verify a digital signature, just a generic ECDSA or Schnorr signature or whatever. And somehow that signature is going to imply correct execution of the smart contract. So I'll give a few examples of this. I'm going to try to be a bit high level, but it's a bit of a tough thing because this doesn't really sound possible without going into the mathematical detail. So, as I hope to argue, if you can do a scriptless script for some smart contract, then you should. But one thing I don't really know is what all can you do. I know how to do a bunch of very specific contracts that I'll go into, but I don't know what the limits are. And I'm very interested to see how far this can go. So this is kind of a research project that came out of the Mimblewimble blockchain, which itself is a bit of a mystery, which is a blockchain design that simply does not have any script support. It's designed to be very private, very scalable. It was invented by somebody using the name Voldemort, who posted a research paper and then disappeared. And an open problem that he left for us was, can we do smart contracts? Can we do scripts? Can we do anything? And the answer is no, we cannot do scripts, but yes, we can do exciting things. So that's where this came from, but I'm actually not going to talk about Mimblewimble at all during this talk. I'm just going to talk about this scriptless script scheme, which is very generally applicable. Okay, so I should first say a bit about why the Bitcoin, Ethereum, Litecoin, whatever model is not so great. So one thing that's great about it is that there are scripts, you can see them, you can execute them, you can see how things work, it's very easy to tell what you can do. But that's sort of the only good thing about this model. All of these scripts need to be downloaded, parsed, validated, executed, whatever, by everybody verifying the blockchain. They're all sort of arbitrary programs. They can't be compressed, they can't be aggregated, they can be expensive to verify. And the details of the script also have to be available to everybody verifying them. So there's maybe a privacy hit or a fungibility hit that comes from doing this. And another thing that I don't mention here, but I'll sort of hint at, is that the rules for script execution have to be consensus rules. They have to be agreed upon by all validators of the system, and changing these rules to support future use cases can be quite a big deal. And if you have a script that works, say, on Ethereum, this might be very difficult to port to something that works on Bitcoin or vice versa, because they have very different models and they have very rigid models. So scriptless scripts are one way to sort of avoid this kind of rigidity. Scriptless scripts, as I mentioned, result in the only data hitting the chain being simple single-signer digital signatures, or what appear to be simple single-signer digital signatures. The verification will remain the same, What I'm going to do is do crazy things with the signing so that smart contracts can be executed, and so that these signatures can't be produced without executing the smart contract. So this is one of my 3 technical slides. So you're welcome to tune out, and I will try to make the rest of the talk make sense without this. But I should first describe what a Schnorr signature is. So a Schnorr signature is a type of digital signature. You have some message, you have a secret key. You can mix these 2 things in such a way that anybody can verify you mix these things, you get a signature, anyone can verify that signature given the message and what's called a public key. Okay, and if anybody changes the message, the signature will no longer be valid. Nobody can produce such a signature except for you. Your secret key and your public key are linked in this way, but nobody can learn anything about your secret key from these signatures. Okay, so one type of digital signature is a so-called Schnorr signature, and why these are interesting is because algebraically these are linear equations. And that's basically, I'm just going to read these and try to only use the word linear, basically. The signature is linear in your public key, and in the second public key that's part of the signature, the ephemeral key pair. It's linear in those, it's linear in the private keys, it is linear in the components of the signature. And what linear means, basically, is that you can add 2 signatures and you will get another signature. Or rather, you will get something that can be verified by adding the verification equations for the signatures. Where adding is defined in some way that makes sense and feels like adding. So that's all that I'll say there. If that doesn't make sense, it's fine. It's just there to sort of justify what I'm going to do in the following slides, where I add a bunch of things and then claim that this still works. Okay? I should briefly mention ECDSA is an alternative to Schnorr. This is used in Bitcoin, it's used in Ethereum, it's used in most all of the cryptocurrencies that I'm aware of. ECDSA does not have these strong linearity properties. So a lot of what I'm going to talk about is much harder to do with ECDSA. So a lot of this is sort of either useful for a future version of Bitcoin or Litecoin, maybe, where we have Schnorr signatures, or it's a research direction into translating this from Schnorr signatures into ECDSA. So unlike all this open timestamp stuff that we're going to see is like there, you can use it now, this is a bit of a researchy kind of thing. But I hope to get people excited about it because there's some really cool consequences if we can get this working. We can, it's just engineering. We can get it working. Some really cool consequences when we get it working. Okay, so let's give some examples. So one simple one that's very relevant to timestamping, which is most of what we're talking today, is this so-called op-return output. And I'm going to describe this as a script because in Bitcoin this is a script, but really what it is a commitment. You can create a Bitcoin transaction, the outputs of that transaction are allowed to commit to arbitrary things, and the way that you do that is you just put a hash in the Bitcoin transaction. And the result is a transaction that is clearly just adding some extra data, it's adding some hash. You can see what the hash is, maybe not what the hash means, what it's committing to, but you can tell that it's a hash, and it takes some space, you've got to verify that it's a hash, and you've got to keep it around forever. So one thing we can do is rather than using the hash as a commitment, we can use this other weird operator, where we start with a public key, and we execute this operation. We hash the public key along with whatever you're actually committing to, multiply that by this element g for some definition of multiplication, add that to the original key, and use that as your key. So one thing I glossed over with Schnorr signatures is you have an ephemeral key as part of the signature. So there are 2 keys in a Schnorr signature, or an ECDSA that you can use. You can use the public key, which is sort of the destination of the Bitcoin output. And if you commit to something with a public key, we call this pay to contract, because what it does is it labels the Bitcoin output, it labels the destination with some data that you're committing to. And so, for example, this is used in the sidechain Elements Alpha to send coins into the sidechain. What you do is you create a Bitcoin output, it commits to some destination on the sidechain, some sidechain address, using this mechanism, and then on the sidechain rules actually verify that this commitment is legitimate. So the Bitcoin people don't see anything. Because you can see what happened. We start with a public key, you do that, but you wind up with another public key. And so as far as Bitcoin is concerned, nothing happened here. It's just a normal public key. But on the sidechain, well, we can see that there's more meaning to this. And this gives a hint to how we can hide stuff inside digital signatures. A variant of this is if you use part of the signature rather than the public key to hide data. And you can do the same thing. You can add a commitment to a signature. And now rather than labeling the output of your transaction, rather than labeling a destination with something interesting, now you're labeling the signature with something interesting. And what that's useful for, as far as I'm aware, is basically timestamping. So if you're somebody who's creating a Bitcoin transaction, and you've got, say, all these people who want to put a timestamp in the Bitcoin chain, you might as well take whatever they want to timestamp, mix that into your signature, put that in the chain. Now you've got a timestamp that takes 0 space in the blockchain and 0 validation cost, because what lands in the blockchain is just a signature that you were going to put there anyway. Okay? So this is not even really a script, it's just a commitment. But I want to demonstrate that, to show that it is possible to do interesting things without expanding past just a single signature. Okay? So one thing that I'll quickly say, because this is a bit more technical than I want to be, is the Schnorr signatures, because they're linear, you can add them together. What happens if you directly add Schnorr signatures is that you get a multi-signature. So maybe I create a signature with my public key, and Giacomo creates a signature with his public key. We can add those together, and the result will be, if we do a little bit of preparation work, a single signature that can only be produced by me and Giacomo together. So this is a multi-signature. You can create a Bitcoin X output that can only be spent by me and Giacomo together. And anyone can verify that it's spent legitimately, but what they verify is just a single signature. So it's only he and I who need to know that really the rules for spending this coin is a 2 of 2 contract. And we can extend this to 2 of 3 or M of N for any M of N. And the result will always be just a single signature that lands in the chain. So there, now we're into something a bit more interesting, right? Because now we've got some rules for spending coins that are some sort of threshold signature where you need a certain number of authorized parties to agree. But again, the blockchain doesn't see that. All it sees is one signature. The most general thing you can do is what's called a zero-knowledge contingent payment. So in the previous slide, I talked about how a signature requires a certain number of people to agree to something. It turns out you can require pretty much any condition that can be computably verified to be satisfied in order to produce a signature. And the way that you do this is using this trick called zero-knowledge contingent payments. This was developed by Greg Maxwell and a few other people. And what it does is, in the original formulation, it creates a Bitcoin script that requires a pre-image of a hash to be posted. And so if I have a solution to some difficult problem, and I want to sell this to somebody, maybe they will send some coins to a Bitcoin output that I can take, but only if I provide the pre-image to a hash. And before they do that, I prove to them using something called a zero-knowledge proof. I give them a proof that the pre-image to that hash is the encryption key to a solution that is correct, that satisfies a problem they want solved. Okay, and this is a very intricate thing, but it doesn't touch the blockchain. It's all just, I communicate with the person who wants to buy this. I say, well, I have a solution, and I've encrypted it to you, and the encryption key is something that I know. And if you send these coins to this Bitcoin address, then I'll be able to take them, but only by publishing the encryption key that you need. And I'm able to prove that using a zero-knowledge proof. And we can turn this into a scriptless script. We don't even need to publish the hash to the blockchain, because actually signatures already have a hash in them. That's the way that they work. The way that signatures work is you hash a message and you maybe hash other parts of the signatures. So there's already a hash in the chain, so why not just reuse that? Why don't I produce a zero-knowledge proof that the hash that I'm signing, my transaction hash, the data that goes into that is actually the encryption key for a solution to some problem that somebody wants solved. And this was actually described by these people from the University of Warsaw about a year ago, before any of this other stuff was invented. And they developed a way to do this with ECDSA, which is a little bit, well, it's quite intricate. It's a very interesting paper, but it's very time-consuming, it's very intricate. Using this mechanism is much simpler. If you believe that a signature has a hash, and you believe that hashes can be the hash of encryption keys in a provable way, then you plug these two things together and it works. Okay. But that's very general, but it's still not something that we know how to do super efficiently. There are a lot of specific problems we can solve. For example, there famously was a Sudoku solution traded on the testnet blockchain about a year ago. But for realistic things, for things that you want to do, I should say, many times a day, or even many times a second, it's not the most efficient thing in the world. So I'm going to move on to more realistic things that people want to use the blockchain for, and that can be done much more efficiently without these zero-knowledge proofs, okay? Or without these zero-knowledge proofs of general computation, much simpler ones. So the first one I want to talk about is, well, it's going to be sort of a building block to many things, to atomic swaps and to Lightning and to many of these payment channel kind of constructions. So all of these are based on the idea of atomic transactions. You have two transactions, maybe two Bitcoin transactions, or maybe a Bitcoin transaction and an Ethereum or transactions on multiple chains, and you want one of them to execute if the other one does, and vice versa. You want these to be atomic. And the way you can do this, if you have explicit scripts, is quite simple. If you can support hash pre-images, you create a transaction that can only be spent by revealing a hash pre-image. You create another transaction that can be spent by the same hash pre-image. And now as soon as somebody publishes one transaction or spends the coins from one transaction, they're required to publish that hash pre-image. The other party can copy that pre-image off of the blockchain onto the other transaction, and then they can move the coins. So I can do what's called an atomic swap, where I'm trying to send bitcoins to somebody in exchange for Litecoins. I send the bitcoins. In order for them to receive the bitcoins, they have to publish this hash. I can use the same hash to receive my Litecoins. So they both go through, or neither of them do. You might think, if you're just looking at the previous slide where I said, hey, we've already got a hash, why don't we reuse this hash again? We can't, for two reasons. One is a aggregate of technical reasons, and the more important one is that if you have the same hash in two signatures, this links the two transactions. So one goal of the scriptless script is that you have digital signatures representing smart contracts, and they're always unique, uniformly random, independent digital signatures. They're valid signatures, but they are not connected to each other or to anything else in any visible way. And if they share a hash, if this were even possible, this would be no good. So we need a different way to do a hash pre-image. Okay, and then here is my second, and this may also be the third technical slide of the talk. So I'll try to make this understandable. And again, I'm going to use this word linearity. Linearity means I can stick plus signs everywhere, and the math works. So we introduce this new, basically a signing key pair, little t and big T. Big T is a public key that you can tell the world. Little t is a secret key. And what I want to do is produce a signature such that when I publish this signature, it forces me to reveal the secret key little t. So that this key pair is unrelated to any of the other signatures, but I'm going to construct a signature that somehow forces little t to be revealed. And the way that I do this is I take this R, which is part of a standard signature, it's a so-called ephemeral key, and I add an ephemeral public key, and I add this new public key T to it. And when I do this, this is halfway towards producing another valid signature. The other half is that I have to change the second part of the signature S. I have to add little t to that. And so what I can do is I can take a signature, I add R plus T to the nonce and produce a valid signature, and then I give the original signature S to somebody. And now anybody who has a signature S can look at it and say, well, if I add T to this, I'll have a valid signature. They don't know what little t is, but they can verify using big T that if somebody were to add this to the signature, they would get a signature. And what this means is that if you know little t and F, you can produce a valid signature. And conversely, if you know a valid signature, you can get little t. So there's a sort of new piece of data, little t, which is independent of everything else. But as long as I give somebody this adapter key, this S where you have to add t to make it valid, then they can get this piece of information out, and I can exchange this piece of information T. I can send that to people using signatures that hit the blockchain. Okay? So that was very abstract, and I'm sorry for that, but let me try to motivate it now with a couple examples of how this works. The first is the cross-chain swap, which I talked about earlier, which normally you do with two hash pre-images, which you have two transactions which both require the same hash pre-image. You can do this with these adapter keys, these adapter signatures. What you do is you create two transactions on each chain. Each one requires a signature. So let's suppose, say that I'm trying to send Bitcoins to somebody in exchange for Litecoins. So what I'm going to do is I'm going to think of this T here. I'm going to think of the secret data. And the person who's given me these Litecoins, before they're willing to sign off, they're going to say, Andrew, I need an adapter signature using this big T. I tell them that, and they know that. I'm going to need an adapter signature on both sides. Meaning, if I sign to take my coins, they will learn this value little t. And using another adapter signature, if they learn that value little t, they will be able to produce a signature where I give them the keys. Okay? So, we do all the setup. Then the other party signs to give me the coins. Well, the way we set this up is that it requires both signatures, using the early multi-signature trick, for me to take my coins. So they sign, I sign to take my coins, then they look at my signature. They use their adapter signature to extract this little value t. They then take that little value t and my other adapter signature and turn that into a different signature on a different blockchain, which they can then use to take my coins. And now we've got an atomic swap. As soon as I took the coins, the other party was able to turn this using the adapter signatures and take their coins. And the exciting thing here is that, again, what hits the blockchain is a signature on one chain. It looks like a single-sided signature, and a signature on the other chain. And they are not related in any way at all. Okay? So this is an atomic swap. We can do a bit more. We can do lightning channels, which is basically an atomic swap on steroids. Or say, again, I'm trying to send some coins to Giacomo, but we're going to do this over the so-called Lightning Network. I'm going to send the coins to Alex, who will pass them to Riccardo, who will pass them to Giacomo. And I want to do this in a way that nobody can just keep their coins instead of passing them on. So what we do in this scenario is Giacomo is not directly taking my coins, he's taking Riccardo's. So Riccardo sets things up so that his coins cannot be taken unless he receives them from Alex. Alex does the same thing. His coins won't be taken until he receives them from me. And I set things up so that I know that this is going to go down this way. So I know as soon as my coins go through, everything's going to fall into place, and in the end, Giacomo will receive his coins. And the way that I do that is using these adapter keys, in more or less the way that I described, except now every step along the way, each party along the hop adds a blinding factor, adds their these B's and C's and D's, which are like the T's before. I can add them because everything's linear, right? Linear means I can add whatever I want, and it works. And it all works out. What happens is exactly as I described. I send my coins. I know that these coins cannot be taken unless Alex reveals some value to me. He knows those coins will then move on to Riccardo by the same mechanism. We'll move on to Giacomo by the same mechanism. And what happens, basically, is for Giacomo to take his coins, he receives a value. Riccardo adds that value to something he knows, who passes it to Alex, who adds it to something he knows, who passes it to me, and I set things up so that the final added together values were what Alex needed to take my coins. Okay? And maybe if you watch the recording in slow motion, maybe that will make sense. But I have only so much time, so I'm going to leave this at that. But again, linear means the plus signs work, and we're good. Okay, everything's linear. All right, so there's some exciting things about this. As I mentioned, these adaptive signatures work across blockchains, right? Because we're just sharing the secret value little t, and it's just a number. You can carry it around. You can even use it across blockchains that use different groups for their signatures. And that's a bit technical. I'm not going to go into too much detail there, but there's something that's a bit surprising if you study this, because the secret value t It's not actually a number, it's a member of some group, and to translate that into a member of a group of a different order is a mathematically quite dubious thing to do. But you can do it. Okay? You can do it and it works. You can transfer money across disparate blockchains. As a second very cool feature, everything I'm doing is linear, it's just adding stuff to stuff. So once the final signatures hit the blockchain, anybody can make up this ephemeral key pair, TT. They can make whatever they want. They subtract little t from one signature, they add it to another signature, and they say, oh, look, these must have been linked. Those doesn't mean anything. Anybody can make that up. And this is indistinguishable from what actually happened, meaning this is deniable. Okay? So all of these transactions are atomically linked, but the way that they're atomically linked is that somebody was sharing these adapter signatures before any signatures were public. Once the signatures are public, the adapter signatures become meaningless because anybody could compute them in the first place. So just the act of publishing the final signatures basically erases any linkage that might have existed between the signatures. So the result is completely independent signatures that all look like single signing signatures that had nothing to do with each other that might be on different blockchains. And all that anybody validates is just single digital signatures. Okay? And to add to this notion of disconnectedness, we can do this reblinding thing, which I sort of hinted at in the lightning thing, where everybody has their own version of T here. We add them all together, and everybody subtracts one part of it. It all works out. This is this word linear. You can just always add stuff. It makes stuff hidden when you add stuff to it, but it doesn't break anything because it's linear. Okay. So I will briefly say, so that I don't keep you here all night, that Mimblewimble, which is this weird Voldemort proposed thing, is the origin of the scriptless script idea, and it is also basically itself a giant scriptless script. The way Mimblewimble transactions work is they replace the input and output amounts with what are called confidential transaction outputs, which are Peterson commitments. These are homomorphic commitments, which are binding and hiding commitments to real values that are still linear. Okay? You can add up all the output amounts, subtract the input amounts, you get 0. That means you have a transaction that didn't create or destroy anything. But because instead of having explicit values, you have these commitments, you don't see what the amounts are. You only see that they sum to 0 and that everything works out. And what Mimblewimble does is it takes these commitments, it reinterprets them as keys, it takes this difference, which should be a commitment to 0, it interprets that as a multi-signature key, which as we discussed is the same size as a normal key, demands a signature with the multi-signature key, which means every participant in the transaction had to sign off on it, and it just signs nothing with that key. As long as that signature was produced, regardless of what it signs, it means all of the participants agreed to participate in a transaction that combined those keys. Okay, and this is something I pretty much need another hour to explain in an understandable way. But it's very magical. And ultimately, it all comes down to the same linearity tricks that I've been talking about this whole time. And the result is a single signature that represents an entire transaction. And the rest is sort of just data that hangs off of it, that can eventually be pruned and deleted, and nobody needs to see it after a time. Or after the outputs are spent, nobody needs to see those outputs anymore. Because the real core of the transaction, the evidence that the contract was executed properly, is contained inside this single signature. Okay. I have a pile of open problems about this, as I mentioned earlier. I don't know what the limits of this are. I guess this is my last one. I wonder about combining scriptless scripts with multi-signatures. So a lot of these are based off of multi-signatures. But what if you have two people, or I should say two parties. Each party is doing some smart contract amongst themselves that should produce a single signature. Well, the way this multi-signature construction works is that those two parties should be able to combine their single signatures so you get one signature representing multiple smart contracts. And I think making this work is just a question of engineering to make sure everybody communicates the right things to each other off-chain. But the consequence of this is that you can not only execute many smart contracts in a single signature, or many different kinds of smart contracts in a single signature, you can actually execute multiple contracts that are independent and can be arbitrary things, and the result is a single signature representing the valid execution of every one of those individual contracts. And this is a very exciting research direction, and I know I can do it for some of the things I described, but I'm not sure about all of them. The second thing is ECDSA support. As I mentioned, in Bitcoin and Ethereum and everything that people use today, we're using ECDSA instead of Schnorr. ECDSA is not linear. Every plus sign I showed you doesn't work, and it was all plus signs the whole time. So there's a hope that we can extend this to ECDSA so that we can use these things in systems that are usable today, rather than waiting around for somebody to propose a Schnorr signature extension to something. Lock times and extrospection. This is something like an oracleized kind of idea. How can you prove that some data that's external to the contract is valid? Well, for data that's actually part of the blockchain, it should be possible in principle to look at that, because it's in principle computationally verifiable. But this still seems hard. And then more general extrospection, you know, who won the World Cup or whatever. That, I mean, you need oracleize for it. But I think we could implement oracleize in something that looks like a scriptless script. I'd have to look at this in more detail. And I guess this falls under the final thing, which is understanding where the limits are. I gave you a pile of examples. They all seem like more or less unrelated examples. And I don't know how to fit this into a single coherent framework. This is very early days. There's lots of exciting research happening. And it's not clear where it's going, only that it's very exciting. Okay. And that's everything. Thank you.
Thank you very much, Andrew. Peter, your turn.
Well, I just have a live demo rather than slides, so I'm sure you're going to see me get very embarrassed in about 5 seconds when I go try it. But let's go start out with the embarrassing part. All right, yell out a word, random word. Word, deal. Goddamn postmodernism. Let's see if any of this actually still works. So the idea, well, word. Let's try show files. A little on the slow side, but essentially what we've got here is, if you're ever familiar with Internet Archive, oh cool, it's actually working, I'm surprised. Let's try download OTS.
Don't say too fast.
Info. Now, I think Riccardo did an excellent explanation of talking about open timestamps, and by now you should probably know it's a general purpose timestamping solution, anchors in Bitcoin, and so on. But it's a lot more interesting if, when you want a timestamp, it's there. And frequently, when you know you need a timestamp, it's way after the fact. Well, archive.org, or also probably better, want me to call it Internet Archive, that is, as the name suggests, an archive of essentially the entire internet. And the way the Internet Archive works is, at the very lowest level, they have a concept of an item. Now, you may have heard of the Wayback Machine, where you go type in, you know, petertodd.org, and you look at embarrassing photos of me when I was like 15 or something, and barely knew how to code HTML. And you can get all these great archives of websites, but ultimately what all this is happening is kind of going onto this big file system of items. And those items, every item has a bunch of files in it. Sure enough, they have an API. Well, with that API, you can do cool things like, as shown here, provide a search interface. You know, this Word 0008 thing. If we click on this, where are we? There you go. I mean, that's actual Internet Archive material. Archive.org, I have no idea what that is. But it is in the archive.
Statistically porn.
And you know, I don't actually know how much porn is on the Internet Archive. And in front of an audience, I don't want to know either. And that is their thing. I mean, it's an MP3, a PNG. I'm guessing this is someone's podcast or something. And we can look at the metadata. There, files.xml. This will even work. Oh, there you go. And you probably can't see any of this, but the important thing is SHA-1 hashes. So with their API, I just went through, starting at 2002, ending at 2017 a few weeks ago, and just grabbed every single file that I could, or to be exact, every single metadata about the file. That's like 500 million files. Kind of took a while, but a few days later it's done, and I get this gigantic file with every single SHA-1 hash that they expose through their API. And well, what do you do with that? Well, you just make it into a Merkle tree. A couple dozen lines of Python, make a gigantic Merkle tree, hash it up, wait about 16 hours, and at the very top you have 32 levels up, or no, what is it, 30 or 31 levels up, the tip of that Merkle tree. What do you do with that? Well, you put it in the Bitcoin blockchain.
Yes.
And that's kind of all there really is to it. I mean, 90% of the work was really the really cool website those guys did. I just dicked around with a bunch of Python scripts and tried to look cool. And it means that, this timestamp you're looking at, this is also another cool thing that they did and I didn't. Based on Andrew Poelstra's work here, to actually show what the timestamp is. And as you see here, well, where's it at the top? There. Document digest, it's the SHA-1 hash, and a whole bunch of append and prepends over and over and over again until finally, where the heck is this damn thing? There, finally, all right. So finally when you get down to here, this is about the part where you actually have Bitcoin, 500 million items later. And there's your Bitcoin transaction, down all the way to the bottom, and eventually you wind up in, there you go, Merkle root of a block. Very simple. I have that for nearly every single file on archive.org, minus a couple that I kind of forgot to do because I had a typo in my import script, but I'll fix that later. And this website here, not this one, not this one. There you go. Basically what we're doing is just provide a nice, easy way of, if you see something on archive.org that you can actually download directly from them, you can also search for it here and get that timestamp. Maybe you want to go show that some guy's podcast went and kind of said something about, maybe something that turned out to be a gigantic scam, and now the guy's denying it. Easy, just go show, hey, that was created well before anyone knew that, quantum cryptography simulations were fake. And you can get that info out. Because it's all automated, I'm going to be setting up infrastructure, keep doing this on an ongoing basis, dump it into my gigantic 90 gigabyte or so database of timestamps. And that's really all there is to it. And take a look at it. This is up on, the source code that actually does this is up on GitHub on the Open Timestamp server. I probably shouldn't say this is all live, but I guess it's live now because you guys can read the URL. And what I'm really hoping, and I have actually been talking to the Internet Archive people about this, is that they'll add it to their site directly. You may have seen earlier my tweet saying, hey, I'm going to do something historic, send me money. And apparently that worked because I got about $300. I'm going to have to do this more often. And that's going to, that all ends up in there. Well, sure enough, of course, Internet Archive people saw the tweet. But how did you do something to all the Internet Archive? The Internet Archive is kind of big, right? Well, sure enough, their APIs work really well, and that's kind of that. So hopefully, this discussion will go further, and we'll actually do this on an ongoing basis, and it'll just be part of their infrastructure. And finally, one last thing I'll point out before some smart aleck says it. A bunch of you in the audience probably know that SHA-1 is broken. It's kind of broken. It's broken in the sense that I can create two messages that have the same SHA-1 digest. But I have to do that at the same time. And remember, what does a timestamp prove? Well, it proves that a message existed for a certain time. If you're really, really clever and you create two messages with the same digest, but you do it at the same time, the timestamp proof is still valid.
Yeah.
So, in fact, we're good to go on that too. Although, because I'm a bit paranoid, I use SHA-256 for everything else. But I think that's really all I have to say about this. Timestamping is really not that hard. And it just goes to show, Merkle trees make everything scale. You know, one Bitcoin transaction, 500 million digests. That's pretty good.
Billion.
Thank you.
Thank you very much. So now we take questions for all the previous presentations. So we can have questions for the hackathon itself, to Riccardo and to Thomas. We can take questions for Andrew about scriptless script. And we can, I don't know if you understand, if you can get up.
First off, I cannot refrain from saying congratulations. It's been really amazing. I mean, such a simple and powerful idea. Really, I'm really nailed. Okay, yes, it's amazing. The question is actually for Andrew anyway, and it's again, it's non-technical. I mean, there are people debating. Okay, Bitcoin was just the first attempt at doing, let's say, cryptocurrency without being precise on words, and further attempt would be much more successful. And my personal stance has always been like, well, this is possible, but Bitcoin might have already too much traction to be really, you know, phased out by something else. Nonetheless, looking at Mimblewimble and especially the way of this kind of scriptless script really make the impression of, gosh, we should do it this way. We should start anew. What is your take on this? How do you feel about that? Can there be some continuity between, let's say, first incarnation of Bitcoin and some superior second design of it?
Now Andrew launches his ICO.
So the wonderful thing about scriptless scripts is that they require only Schnorr signatures, and maybe not even that. Which means that if Bitcoin were changed today to have Schnorr signatures, and then we could do everything that I described today in Bitcoin, in the existing Bitcoin system. And adding Schnorr signatures is not technically difficult. There are a couple ways that you could soft fork this into the Bitcoin system. I think with these kind of use cases and people saw this power, it would probably be a fairly easy sell for the community. This is a type of digital signature that's been around for 30 years. It's got an academic proof that it's a secure signature, unlike ECGSA. It's more efficient for a pile of reasons. There are many reasons to want Schnorr signatures, and it's not very difficult or disruptive to add them. So I think it's perfectly reasonable to see a future, the near future even, well, in the next year or two, where we have Schnorr signatures in Bitcoin, and then we get all of this wonderful stuff. So there's no need to have another system. There's no need to have a separate Mimblewimble system just to get scriptless scripts. And this is a lot of the power of Mimblewimble just in these scriptless scripts. Secondly, the nature of scriptless scripts is that because they all look like Schnorr signatures, when you discover new types of scriptless scripts, anybody can go use them. The result is Schnorr signatures. You don't need to change the system at all. It's still Bitcoin. So we have all these directions in which Bitcoin can move that would get us all of this cool stuff and more. So no, I think I wouldn't count out Bitcoin anytime in the next 100 years. I mean, and you can timestamp that.
Other questions? You're shy. You had like 31 questions the other meetup. Really? You're intimidated.
My one's too simple and his is too smart.
So we can get directly to the final greetings. If you have questions that you need some time to elaborate, which is kind of probable, it will work that way for me. Then we can pass to the final greetings. Actually, I would have another question for Peter, and probably I will also ask at this point. I will also add or ask some more details about the hackathon so that everybody can have all the information involved here. So my question will be, that's a very general question. One of the things that Bitcoin made possible was actually a trustless timestamping and proof of publication that made possible to have an independent proof of anti-double spending measure. The idea here is actually it could also be for Andrew, but I will focus more on Peter. Do you think that having this much part of the consensus rule taking care of all the validation process and not just of the proof publication is helping somehow also the coordination between solutions and the social scalability? What I mean is, if you use so much this part of Bitcoin and you start to loosen a little bit all the parts that are validating script on chain, multi-sig on chain, don't you have the risk to have standards diverging and less social momentum on a single standard? I mean, not scalability, technical unscalability of the protocols like Ethereum as an extreme and as Bitcoin. It could not be a feature of social scalability of the same standard because all the nodes have to do the same kind of work.
So I'd say, this is actually an interesting problem with Ethereum, where you see all these very interesting smart contracts, but when you go talk about a smart contract, a lot of the effort to actually create an interesting smart contract is not writing the little thing that kind of ends up on chain. It's writing all the software around that thing that actually makes it useful. Because, you need GUIs, you need network protocols around it, you need all this stuff that's not actually in the consensus. And no matter what you try to go put in the consensus, you're always going to have the software around it where you can go disagree about it. So I think what you're not wrong in that, yes, you have these kind of problems, but I don't think there's any way to solve them. No matter what type of system you have, unless you are getting mind share by some means of all people using one single solution, it's always possible for people to use different solutions. It's only when you're doing something really, really simple, like paying from person A to person B, is it all that easy to get that kind of mind share. Whereas the moment you're doing something a little more complex, like, all right, I'm going to have a payment protocol for, say, paying for a movie. You will have an inevitable fracturing of the ecosystem because, well, maybe my movie payment protocol can work a little better in this way, and your song payment protocol would actually work a little better in that way. Well, inherently, there's going to be developers going to say, well, why should I, have the limitations of his protocol when I can optimize for my protocol? Why don't I go do a better job? They will write that code. You can't avoid that. And since they will write that code, you will get that incompatibility. Whether or not there's a chunk of that code sitting on a consensus protocol doesn't change the fact that everything above that, there will be an incompatibility. Much the same way as like in Bitcoin right now. You think we have one address format, but we don't. We have addresses starting with 1, addresses starting with 3, which took forever to get deployed. Even though it was such a simple thing, yet it still took a while to get that mind share. Plus you get things like stealth addresses, which again are an improvement on payments, but unless you have that as your use case, you're not necessarily going to write that code to add it, so you fracture the ecosystem. And in case the stealth addresses was fractured enough, people aren't really using it too much, if at all. I mean, there's no, even though they all use the same consensus system, they still have different UIs. So really, I would say that these kind of systems, the advantages of letting people go innovate and figure out what is the right solution, rather than having to ask 100 different other people, hey, do you think this is a good idea, or are you going to adopt it? Much outweighs the fracturing that's going to happen anyway.
Thanks. So, I will also ask the last question. That will be for Riccardo. Business model of Eternity World is to help people timestamping stuff. So now that if you write something on Passbean, it gets automatically timestamped because of what you did today. What will you do for a living?
Go on vacation. Another ICO. There are a lot of stuff, new stuff. going on, private stuff, and
Companies hiring.
yeah, I mean, most of the use case of timestamp is also for private stuff, which does not finish on the Internet Archive. And yeah, while it's a good, the best thing you can do by timestamping Internet Archive, there are, you know, point in time, and there is not all Internet.
Yeah. And also, of course,
Yeah.
it was a joke, half joke.
Yeah,
But that's very interesting. Also, that's part of a general model of Bitcoin startups that continuously how to self-disintermediate all the time. The Bitcoin work is like, I will create this, I will put the code open source, and I will remove the need of my own services.
And it's better that you be the first, otherwise, otherwise some others, you know, if it's possible, some others will do. Yeah.
Absolutely. I will ask also maybe Thomas and Riccardo to give some details about how to subscribe. Is it still possible to subscribe for tomorrow? Yes. Okay. So if you give some indication of where to go.
Yeah, that's a good point, because we realized like half an hour before the start of the event that there was no link on any presentation. So if you want to come at the event, just look on Google for Eventbrite Bitcoin building layer 2 applications that matter. It should be easy to find it, or just come to me or Riccardo and we will help you. So please sign up if you.
Are there still tickets available?
Yeah, there are still tickets available. There is also a webinar, so there's going to be a live stream for the workshops, not for the hackathon, of course. So if you cannot make it to come in person tomorrow or the day after, you can still just attend online. Of course, it's much better for having some kind of real-world interaction to come here in the next few days for the workshops. But of course, for the hackathon, there is a lot of fun to come, so please come in person. Thank you.
Thank you. Okay, final greetings. Now we have with us Adam Gibson, who is working basically on Join Market, which is a very cool privacy fungibility application. I don't know how many of you tried to use Join Market to get more privacy. Okay, and I know so Peter, and that's very cool. And also we're now also working on CoinsWalk. So thank you for being here.
Thank you. Yeah, so I suppose I should just say a few words about what Join Market is, because I'm sure a lot of people don't know what it is. So as you all know, fungibility and privacy are big, very big issues in Bitcoin especially. And CoinJoin is one way that you can improve the fungibility and the privacy, or a fungibility boost from doing that. So yeah, Join Market's been going on about 2.5 years now, 2 years on mainnet. There's a fairly small group of people who use it. It's not particularly user-friendly, we could say that. So if you want to help out, either take part or help out with development, please feel free to contact us on Reddit r/joinmarket, on IRC, Freenode, Join Market. Yeah, just take part. I'll also mention, because an issue that's come about recently with CoinJoin and Join Market is because fees on the Bitcoin blockchain are getting higher and higher. It's becoming more and more expensive to use this kind of approach to fungibility improvement, because it involves very large transactions. So I've started looking at another proposed fungibility improvement called CoinSwap. They were actually both proposed, I think it's fair to say they were both proposed by Greg Maxwell at almost the same time, in late 2013. But nobody's really looked very much.
Why sleeping?
Yeah, exactly. Right. But nobody's really looked much at CoinSwap. I think there are reasons for that. As it turned out, it was kind of broken anyway. So I've kind of made a tweak to it, and I'd like anyone else, if you're interested, please get involved or talk to me or look at it. You'll find a repo on GitHub, CoinSwap CS, under my username Adam IS Z or Z if you prefer. Yeah, so yeah, basically please get involved, and consider that if you use joint market, you may actually be contributing some funds to Peter Todd. So either that's a good thing or a bad thing. I'm not sure. Okay, thanks.
Thank you. So now, for the second meetup in a row, I will call to tell a few words Ken Shishido, that I always call for final greetings, because other than presenting always new interesting projects, he always learn new Italian to tell to the meetup. So I'm sure you have another sentence that you want to tell to them. No pressure.
Sono ancora qui. Mi piace il Milano. Well, yeah, a lot of things happening. Things are moving very fast in Bitcoin space. I guess universal thing, price go up, more people come to the meetup. And some recent news in Japan is that one of the exchange yesterday hit $10,000. And they have executed some trade, and they had to roll back. So people are going crazy. And, right. And the other thing is, another exchange announced that they will pay 5% earning interest on Bitcoin saving per year. That's a great deal. This will drive a lot of people, especially senior citizens. They come into Bitcoin land. And it's interesting that when this exchange checked with the financial agency, that they said they will pay 5% interest, right? But they said because Bitcoin is not money, it's not regulated, so they can do that. Isn't that great? So the legal status, as I mentioned last month, in Japan, is Bitcoin is currency-like property without VAT tax. So there is no regulation on interest payout. So, and the exchanges are adding to the tune of 1,000 to 2,000 new accounts per day. So it's really rocketing, going up. And last thing I noticed, I really laughed this afternoon, is that there are new people come to Meetup, our Meetup page, and one guy said, I have this question, how did you know about Bitcoin? This is a question I have in the meetup.com page. And this guy said, I heard about Bitcoin when I searched blockchain. So the world is completely going upside down.
Bitcoin is the new blockchain.
Yeah. So thank you very much, and buonasera.
Thank you. So now, from not so far east, but from Middle East of Europe, yeah, we know that tomorrow we will have the first part of the BitHack, the HackBit with Riccardo at 6:30 p.m. Before that, still in Blockchain Lab, there will be a presentation of Open Bank IT. And we are here just to say hello and to give you some indication of what it is. Pavel Kravchenko. Pavel is one of the organizers of the blockchain and Bitcoin community and activities in Kiev and Kharkov in Ukraine. They are known for a very good conference that they are different from ours because they are also fun party at the end, so we have to improve on that. And they are here to present tomorrow this application. It's not strictly Bitcoin related, but could be interoperable in many ways. So thank you, Pavel.
Hello. It's good to meet everybody. It's my probably 7th time in Milan, and I enjoy it. And I'm Pavel Kravchenko. I'm from Ukraine, from the company Distributed Lab. So we are R&D for blockchain and for decentralized technologies. And small background about why we are doing that. We noticed that world is perfect in terms of information exchange. We have internet, you can send message overseas in a second and for free, no borders, but it's not working for money or for assets in general. And so people are still struggling with that. And Bitcoin and every cryptocurrency is a great prototype of what should be in the future. That's what we see. We believe that it doesn't need to be a single blockchain or even blockchain to actually let people exchange value. So basically we think that there should be protocols that something like HTTP and software, something like Apache, that will drive payments and reconciliation between companies in general. And thinking about that, we are specifically working on open source software to power organizations that deal with assets like banks, e-money companies, loyalty providers, complementary currencies, and like some digital assets in general. We provide them with software that let them connect to each other and serve their users. In particularly, we have a separate company that we created together with bankers to produce software for digital banks that is going to be, it's already open source and free, and let banks save quite a lot of money on building the whole digital infrastructure. It's not about cryptocurrency, it's more about digitizing all assets. So I will be talking about that tomorrow at 4:30. Yeah. Thank you.
And good night, everybody. And if you have other questions for the guests, just approach them. After they can at least drink a spritz. Then after you can approach them. And the next meetup will be with Rosbeef, right? We already know the date.
7 probably.
7 of June. Okay. Good night, everybody. Thank you.
Yeah.
Guys, if you can come here for the final picture.
Yeah. So.